Hello and welcome. Thank you for taking a look at this video lecture here. I'm going to be discussing about the common emitter circuit. Now, between the common base, the common collector, and the emitter feedback circuit that we looked at, the common emitter circuit is the best out of those biasing circuit arrangements for a transistor. And we'll take a look and see why. Notice that our base terminal is grounded, and now we have two voltage sources. We have a plus VCC of plus 15 volts, and you need a separate or second voltage source, VEE, which is minus 15 volts. So it's minus 15 at the emitter end, plus 15 at the collector end. You need two separate voltage sources. You cannot just piggyback off of one. Now, there's two ways you could go about solving this circuit. One is you don't even need beta, or you don't even need to use any formula that incorporates beta into it. So right there, that tells you that this is a pretty beta independent circuit. So meaning that as beta fluctuates, your common emitter circuit should be pretty stable. It shouldn't really fluctuate. One of the values that are nice is for a common emitter circuit, the emitter voltage is always equal to roughly about minus 1 volt. And this is due to small voltage drop across your RB resistor and your forward bias base emitter junction. So no calculation is required. If you ever have to see this for a test, common emitter circuit, just remember emitter voltage is always approximately equal to minus 1 volt. Okay. So here we're going to look at an example. We'll look at the first way to solve this. We have a VCC of plus 15 volts minus VEE at minus 15 volts. We have an RE resistor of 10 kiloohms, an RC resistor of 4.7 kiloohms, and RB resistor of 47 kiloohms. So VE is roughly equal to minus 1 volt. Now let's look at determining what is the emitter current. Well, it's going to be the emitter voltage. What is the emitter voltage? That's everything at this end right here. So we have a minus VEE, so minus 15 volts, and with the minus in the formula, we would end up having minus times a minus 15 will give you 15 volts, minus your 1 volt from the emitter voltage. Because at the emitter end, you have two different voltages to worry about, this VEE and your VE value, which is right here, which is minus 1 volt approximately. So you have 15 minus 1 over your RE resistor of 10,000 ohms. So we end up with an emitter current of about 1.4 milliamps. Now we could calculate VC because once again we could also approximate IE and IC to be equal to each other. So VCC is plus 15 volts minus our 1.4 milliamps, which is what we just calculated, times your collector resistor of 4,700 ohms. So we end up getting a VC of about 8.4 volts. If you put this in your calculator properly. Now we could calculate VCE by taking our VC of 8.4 volts minus a negative 1, which is what our VE is. So you have two minus signs to consider. Minus from the formula and a minus from the voltage value of the emitter voltage. So this becomes 8.4 plus 1, or a VCE value of 9.4 volts. So that's the straightforward way to solve this. Now we could demonstrate using this formula, where this is kind of similar to what we saw in the emitter feedback bias formula, where we have a minus VEE minus VBE, which is the 7/10 of a volt, over the emitter resistor plus RB over beta. We could use this to prove that beta really doesn't have any major fluctuations or significance on the emitter current or your VCE values. So we'll do that. So we'll do that down here. I accidentally moved our VC, put it back. All right. So now what we want to do is we want to use the same circuit as above. So I put all the values here, RB, RC, RE, VCC, VEE. And using this formula here, minus VEE minus 7/10 of a volt over RE plus RB over beta. We want to calculate our IC when beta is 100, our IC when beta is 200, our VC, our VEs, our VCEs, and then look at the percent changes. So we're going to assume that the percent changes aren't really going to be significant at all. They'll probably just be, maybe like around 1% or just under 1% changes. But we'll see what happens in the calculation. So let's get started here. So we have a minus from the formula. Minus 15 is our minus VEE value, which we subtract by 7/10 of a volt. Then we're going to divide that by our RE, which is 10,000 ohms, plus our RB, which is 47,000 ohms, over our beta, in this case, of 100. Over here, we'll do the same thing, minus 15. So these two minuses are basically going to turn this into a plus 15. So it'll be plus 15 minus 7/10 of a volt, which would give you 14.3 volts in the numerator. So you have 10,000 plus 47,000 over our beta of 200. And if we look at the collector currents for each, if you put this in the calculator properly, you should get about 1.37 milliamps. And when you do them when beta is equal to 200, you should get emitter current / collector current of about 1.38 milliamps. They're pretty much the same. They're pretty equal. So now we could find VC by taking VCC minus ICRC for both. So our VCC is 15 volts. Our collector current is the 1.37 milliamps, or 0.00137 amps, which are the same thing, times our 4,700 ohms. And our VC value should be 8.56 volts. For here, same idea, 15 volts minus 0.00138 amps times 4,700 ohms, and we should get a VC value of about 8.51 volts. Now, if you want, if we really want to, we could calculate VE. We really don't have to, because we already said it's roughly equal to 1. But if you wanted to, VE is made up of VEE plus the voltage drop across the emitter resistor. So that's IE RE. It'll be the same thing over here, VEE plus IE RE. So now our VEE, is minus 15 volts, so I'll just show it for both here, plus our IE was found to be 1.37 milliamps, or RE is 10,000 ohms. And then over here, it's 1.38 milliamps, or 0.00138 amps, which is the same thing, times 10,000 ohms. And we should get a VE value of, over here, of minus 1.2 volts. And then over here, when beta is equal to 100, we should get about minus 1.3 volts, which is pretty close to minus 1 volt. Then we could calculate VCE just by taking your VC minus your VE. My VC is 8.56 volts minus negative 1.3. Here, it's going to be our VC of 8.51 minus a negative 1.2. And we should end up with the VCE over here. When you basically these two minuses become a positive, so it's 8.56 plus 1.3, which should give you 9.83 volts. And then when we do the same thing over here, we should end up getting somewhere about 9.71 volts, because these two minuses right here will become a positive. 8.51 plus 1.2 should give you 9.71 volts. Now we could calculate our changes in collector current by taking our IC2, which is 1.38, minus 1.37 over 1.37 times 100%, and we end up getting a deviation, or a change, of 0.73%, which is just under a 1% change, which really isn't bad. Now let's look at the percent change in VCE. So it's 9.71 minus 9.83 over 9.83 times 100%. And if you put this in your calculator right, we should get a 1.22% decrease, which once again isn't that bad. This is the reason why the common emitter is wildly popular over the common base, common collector, or emitter feedback circuits. This is how you go about solving these circuits. You have two different ways to show it. One way doesn't even use beta in the calculations. The other way uses beta in the calculations, but you could see that the values are roughly the same. Now that concludes our common emitter lecture. I wish you luck with this type of material. I hope you found this video very useful, and I hope to have you around for future video lectures. Thank you and have a good day. Bye-bye.